think it'll be fine. But
Give me
um,
1 second to move that backpack.
yeah, sounds good.
All right, here we are.
Great. So did this work? Yes. No. Oh, awesome. Yes, we are up. We are live. That's cool. One thing Oliver always recommends is pulling up chat.twitch.tv/TheForkJoin so you have access to the chat also. I'll keep an eye out and make sure if there are audience questions, I relay them. Again, we tend to do those towards the end, and sort of like
Chat.twitch.tv
slash the fork join.
slash the fork join.
Yeah, I think that's how that works.
Oh, interesting. Can you send me a link over the Zoom chat?
Let me make sure that actually works. Nope. Maybe it's a slash chat. Oh, we'll try the final variation, which is chat at the end, and in fact, that is the correct one. Cool. And I'm briefly going to mute myself and turn up the volume on the stream just to make sure you're audible there, and then we'll start. So I'm muting now, and
Sounds
then in
good.
3 seconds, you should say something.
I'm saying something so that I'm audible on the chat. Hello, chat. I've never said hello, chat before. How lovely.
First time for everything. Okay, everything sounds good. You can unmute yourself, and I think we can get started. So yeah, I think people will keep streaming in. I think we have a couple of people around, and then eventually, hopefully more. But super excited to host Mae Milano today. Mae is a professor in the computer science department at Princeton and works at the intersection of programming languages and distributed computing. And so we should just get right into it. And I think one of the first questions I want to ask you, May, so if I understand correctly, your background was initially in programming languages and you sort of slowly have moved towards distributed computing. This is always sort of like an interesting thing when PL people move and become domain experts. So I want to sort of understand what got you excited about being a distributed computing person and what kinds of connections were the things that sort of inspired you to connect PL and distributed computing?
So it's sort of the opposite, actually.
Mm,
I started out interested in distributed computing and operating systems with some amount of security. So when I was applying to my PhD programs, I was writing in big, like, I'm here for systems. My like red letters all came from systems people. And when I showed up at Cornell, I had just actually seen a talk by Jean Yang, who at the time was still a PhD student, has since become a Carnegie Mellon professor and then started a startup, and then a startup got acquired. So she's had quite the journey as well.
right.
And Jean Yang basically gave a talk that said all of these problems are problems that compose. Every
Mm,
time you have a security problem, you have to worry about interaction. Every time you have a systems problem, you have to worry about what is the programmer going to do? Is the system open or closed world? How is it going to evolve? And that means you need to have abstractions, you need to defend abstractions, and you need to communicate those assumptions across a wide variety of current and future programs. And the best way to do that is programming languages. So
interesting.
using a new programming language that actually has a notion of what is the security of this bit, using a new programming language that actually has the notion of how consistent was that read, allows you to actually responsibly interact with the guarantees the system provides while also not tripping over yourself trying to guess as to why your memory looks like this today.
Right.
So I
So
got into programming languages to solve system problems. Like the goal was like I have the suite of things that bug me in systems. I think this is the right technology. And then I liked it a lot. So I kept doing work. And eventually, towards the end of my PhD, did programming languages work for programming languages' sake.
right. So the lens is actually so you like viewing sort of uh, problems through the lens of programming languages, but fundamentally you care about solving distributed computing problems and or sort of systems problem even more generally, not just distributed computing. Um, You referred, I think, very briefly in this answer to this paper of yours that I really like, the MXT paper, which talks about consistency. So very briefly, can you give an overview of what consistency is to folks who might not be familiar with the idea and why it's important? And then you can describe this very beautiful idea in the MXT paper.
Sure. I'm glad you like the paper. So the modern web applications ecosystem is made out of a bunch of like different application servers, which all communicate by reading and writing things to storage, mostly. If you think about like functions as a service, or if you think about web workers, even JavaScript that runs on your web page, what it's mostly doing is doing some local computations based on information that it retrieves and sends to some background storage. And if you're going to build an application the scale of something like Facebook, that background storage is not going to be one server. It's going to have to be replicated. Probably it's going to have to be geo-replicated. And as soon as storage is replicated, you have to ask the question of, does every individual replica or every copy of that server have the same view of the data? So let's imagine that I and you, just the two of us talking right now, are both attempting to store redundant copies of some user data. And the user contacts you and writes, say, x equals 7. At
Wonderful.
that instant, you and I disagree on what x looks like. The user told you, it didn't tell me, silly user.
Right.
And we have a choice here. You can tell the user, hold up, I got to tell my bestie, and
Right.
wait until I've confirmed that I actually know the result. And then you can say, okay, you're good, I actually got it. Or you can say, I got it, and in the background, tell me later, and try to stay up long enough that you can do that. Depending on how you approach this replication and also how much metadata you wind up tracking for it, you get different guarantees about what you'll read on some replica after having performed a write on some other replica. And those guarantees are basically referred to as the consistency guarantees, or how consistent a different reads across the world will be.
Right. So the model is fundamentally that you have a really big application and there are different people coordinating with the computation and the storage parts, right? And
Mhm.
the storage itself is distributed, which means that someone might choose to write to distributed store A, but that information has not yet propagated uh, to the other stores that you might have. And consistency fundamentally refers to sort of the choice you make about how you want to order the propagation of this information with future actions on this store. Is that an appropriate explanation? And so, go ahead. You took a breath in, so maybe there's something I missed in this.
I was just going to say, yes, it has, other aspects of it, but it's really just about what is the protocol that the individual storage node is going to run um, in response to getting it right. And when we model
Mhm.
it, when we formally write it up, we talk about ordering writes and reads in the system. But if you look at how databases tend to be implemented, they tend to be very much an implementer's mindset of like, you will be replicated at 3 sites. What does that mean
Mhm.
for your application? That's up to you.
Interesting. Right. And so the way you've described consistency as a question, and this is related to why I enjoyed this paper specifically, is that it's a system level concern, right? If you're designing one of these applications, something like Facebook, you as the system designer sit down and you're like, all right, what is my consistency guarantee? And you basically, at least this is my understanding of the space, you basically make a decision of what guarantee you want, and you set that up in your store. And then the person who's writing the application code, they all they get to do is assume that you give them that guarantee, right? They're sort of the system designer who's made this decision for you, and the application person is just sitting on the side, uh, you know, on the whims of the system designer. Um,
Yeah, that's the
is
best case scenario,
hmm. What is the
unfortunately.
average case
So
scenario, actually?
the average case scenario is, like I was saying before, that things are a little bit too implementation minded.
Mm,
So there is the ability to ask for strong consistency, which basically corresponds to all the behavior is exactly the same as if you had one single server, and the replication happens transparently and doesn't affect what you can read and write. But as soon as you step away from that, you'll get things like configurable quorum sizes or number of sites. And it's not remotely clear how setting those as a user will correspond to the various guarantees. If you wanted to ask yourself, what can I read after I performed a write? You'd love to know some sort of consistency model that tells you in those terms what will happen. But what you get is like, how many nodes will I contact before I give you a write commit?
Oh, that's very interesting. So what you're saying is that users generally may not get the knob that you're describing, which is very formal and clear and well specified, which is like it's strongly consistent, which means everything pretends to be a single store. It's actually a knob is like I will replicate my information to five of my friends, five of my related data stores, and then I'm going to just continue working as if that was enough. And the question you're asking, which is really interesting, is that how do those knobs actually map to the guarantees or the mental models that people care about? Um,
Yeah.
and so, what do people do? What do people think about when they try to use these systems? Like, I assume there are sort of best practices in this space where they're like, okay, quorum of five, probably a good idea, or like, maybe 50. I don't know.
It's changed over the years. So when I wrote MXD was 8 years ago.
That's right.
That's It's been a minute. I guess it was 6 years ago that it was published, but the design was largely done about 2 years before that, so almost 8 years ago.
Mm,
And at the time, there were basically three pathways that people took. The people who cared deeply about consistency, they would use a database like, say, Spanner, and they would turn the knob up to 11 for as consistent as possible, and they just figure out how to work with it.
mm,
People who cared more about availability than correctness, which was a lot of people, would
mhm,
take something like a MongoDB style database, and they would just think, how likely is it that three different servers will fail at once? Do I think that's likely or unlikely? I think that's unlikely. So I'll set my replication to three,
mm.
which would give them the guarantee that individual write operations weren't lost completely. But they basically were just kind of fingers crossed, hoping there weren't conflicts caused by racing writes to the same location. Because if there were
Right.
conflicts, they didn't really know what would happen. These databases tended to give some flavor of eventual consistent guarantee for resolution, but they were always a little bit different. Like the one that Mongo gave you used the timestamping last writer wins idea, but the one that Cassandra gave you also said last writer wins and did something different.
Mm,
And there are even some databases that didn't do reconciliation. When Postgres first got its multi-master replication mode, if there was a concurrent conflict on two writes to two different sites, you just get an error and the programmer would need to deal with it.
that's very
Um,
interesting.
so it was a pretty bad space. More recently, some consistency models have gotten popular enough for them to be offered as first class primitives. In particular, there's this model called causal consistency that basically says if I perform a write and you perform a write and we're concurrent, neither of us could have known about each other's writes, then they can be ordered arbitrarily, no matter what order they appear to have showed up on.
Right.
But I will at least get the guarantee that if I perform a write, it'll appear to occur after everything that I read when I was computing that write.
I see.
So, from my perspective, at least my own causal history, the stuff that might have been the reason I wrote this, will be ordered before me. So, it will have appeared to have taken effect before my operation does. So, these days, you might see databases like early versions of Cosmos, I think probably still in Cosmos, that'll allow you to pick like one of five consistency models. And those are much nicer because they don't say replication factors or at all. Um, if I look at the most popular systems research coming out now, what you usually see is there's going to be some set of really strongly consistent configuration-y data, like maybe file system metadata or handles, and that gets stored in etcd or Zookeeper, which is a linearizable, very, very consistent database,
Right.
but only really works for small things.
Mhm.
And maybe there'll be some like data that I'm ingesting and I happen to know is going to be just all independent, and I'll throw that in like a big table-esque, very inconsistent data store, but I know conflicts are impossible. And maybe I'm going to be ingesting some data that I think is going to be highly transactional. So people are using it all the time that might have high conflicts. So I'll put it in like Cicada or Cockroach. And you
Mm.
get this sort of mishmash where there's five or six different databases that are all being used and that are being selected partially for their performance and partially for their correctness guarantees.
Interesting. So the way you've set up this space, there's a question that arises, which is if I want to build one of these applications and there's this gamut of there's this big like cornucopia of choices in front of me and there are different trade-offs, right? You've sort of talked about a couple of axes already, but there's performance, obviously, you care about performance. You care about consistency, which is basically a correctness condition, right? Like if I build one of these big things, how do I reason about it? And then you've also mentioned availability, which is perhaps a reliability guarantee that you want. And then there's the nature of the operations that you're doing on the database itself or the data store itself. So,
Mm-hmm.
are there ways people sort of formally think about how to pick various points in this space, right? Like you mentioned a couple of different databases, right? Like if I was to draw a three-dimensional graph, I'm sure these points span somewhere in the space. How should I think about picking the right point for my application if that's something I care about?
So one of the points I was trying to make is that most applications will pick 7 or 8 different points,
Oh,
depending on which part of the data they have. Like the list I was giving of like use etcd for this, use spanner for that, use bigtable for that. That was like one application that
oh,
happened to be, storing its configuration somewhere, storing its basic ingress data somewhere else, and then storing its high frequency data a third place. If I'm, for example, a Zotero style library
mhm,
where I've got core system configuration information, like where are my replicas, what machines are up. I've got individual data blobs that people are giving me. And then I've also got notions of like accounts and collaborative aspects. Those have 3 different basic performance and correctness requirements. One of them really needs to be high performance, really needs to be high availability, and really needs to be correct. The stuff that is my actual system configuration. Because if that goes haywire, it's really hard for me to recover. So that tends to be in
right.
one database. And then when you're spewing PDFs or large data blobs at me, they're probably not going to conflict. And if they are, I just duplicate them. So I can throw
Mhm,
that in a weekly consistent store. But your user account metadata, that goes into a more traditional database because I might want to do transactions over it. And so your application is sort of smushing together multiple distinct, largely mutually unaware underlying databases or underlying data storage systems.
interesting. So maybe one way to frame this is this, like in the same way that your programs have different kinds of data structures for different users of the data that you have, right? You might have graphs, you might have arrays, you might have uh, state variables, local variables, and so on. We should think about applications as being composed of little building blocks. And I think this is a nice segue because the way you describe them, these building blocks are all sort of separated. That's what MixT does, is gives you a way to reason about all of these blocks together and how they communicate. So do you want to very briefly describe what MixT did and why it was sort of a important idea? I have my own perspective on it, but I want the author to speak first.
Sure. I will sort of finish answering the question you asked before first.
Mhm.
How do people choose? If they're choosing multiple or single, how do they choose? What I've observed is that people largely use it by examples. They hear that this is the good place to put configuration data, so they put it here. They hear that this is a good place to put user accounts, so they put their user account logic there. It's, again, like you were saying, almost data structure driven. It tends to be the sort of thing where people think about what kind of data are they storing, and from that derive what kind of correctness will it need. Maybe without even explicitly thinking about the correctness aspects, just thinking like, clearly I have application data type A, so I use the storage system everyone uses for application data type A. Um, Now, in terms of what MXC does, let's assume for a moment that this whole I have application data A, therefore I use storage A actually does work for correctness for application for that application data. That if I'm managing a collaborative document, I probably need exactly the correctness that Google does, so I just use whatever they used. Um, what is harder to reason about is the composition of all of those things. When I've got, data stored in 4 different databases, all of which come with 4 different guarantees, and I'm using them in the same application, what's sort of the composed overall consistency or correctness of my application? If I make a decision about whether to ban a user based on the information that they've uploaded to me, is that going to be correct? Or is there some sort of anomaly somewhere in the upload
Mm,
that is possible, but isn't possible under the user database model? So I'm actually doing it speculatively, and one database might correct itself later and the other one won't.
mm,
MixD's whole point is to try to bring some sort of sanity to building a composed application out of all of these distinct underlying storage systems with distinct consistency guarantees. It gives you a lightweight shim and a custom transactions language that, when you compile it, tells you either the composed consistency of the system is correct or the composed consistency of the system is not correct. Now, correct, of course, is a fuzzy and very opinionated word. What we decided to set correctness as is this notion of sort of projection correctness.
mm,
If I only looked at the most consistent storage system in the application and I just ignored everything else, what is the consistency the application gets out of it? And we took the assumption that programmers would need a property, that strong outputs are staying strong, or strong components of their system are strongly consistent. because they picked that store for a reason. Probably they wanted the guarantees it came with. So what we guarantee is that the interplay between weakly consistent storage systems and strongly consistent storage systems can never cause a violation of strong consistency for the data that comes from or goes to strongly consistent storage.
Right. It's sort of like, in concrete terms, if I'm deciding to ban a user, I better make sure that it's not because of sort of some sort of glitch in my system or my data store, right? Like I should make sure that the decision to ban a user or some sort of like irrevocable like change to my system is based on knowledge that has had time to propagate through the rest of my system. It's sort of really, philosophically, it's like making sure that the knowledge is managed in the way that you expect it to manage. Whereas, again, if you're uploading a PDF in the example you gave, it doesn't really matter how long it took or if the data was duplicated because it's a PDF, right?
Yeah, the
Um,
nightmare scenario in this particular example is either a flapping or a bad decision.
mhm,
So let's say that you uploaded a piece of information that my usage policy says you can't possibly upload. Some terrible thing, and I'm not trying to say you are going to do such a thing, but a generic user comes along and uploads some terrible thing. And the
right.
system running on that particular replica immediately reacts automatically and bans you.
Mhm,
And then you go, what the heck? Why did that happen? You happen to be on a plane, you connect right back to the service and say, like, I want to challenge this ban. And your request hits a different replica that has not
right.
seen your bad upload. And that different replica sees the ban because that happened in a strongly consistent system, but doesn't see the reason because that happened in a less strongly consistent system. So
Mm,
it actually automatically overturns your ban. And now either
interesting.
when you land, you get rebanned, which seems bad, or worse, when you land, the whole ban challenge flow has completed and you'll never be banned.
Right, because this ban that got revoked without having the right information of the cause, there's no sort of like paper trail for why it happened. I see. Right. So it's sort of really the reason you want these strong causal guarantees essentially is you want to be able to trace back the history of what happened, right? That sort of makes perfect
That tends
sense.
to be why people, yeah, why people choose causality, but it doesn't necessarily have to be causal. Let's imagine a different example. I'm running like Super Smash Brothers online tournaments.
Or-
And generally speaking, I'm recording wins and losses of players around the world, calculating your ELO scores all the time. So when you pick up
Right.
your Switch and you play on online ever, you're getting a win loss record. And probably I'm going to use weak consistency for that because I don't want the entire world to have to totally order who wins and who loses random quick play matches on the internet. That
Mm,
would slow down my application for no reason. It's kind of okay with me if I don't know that my win over you in a particular video game has propagated instantly around the world. But if I'm going to use that data to do something like have a tournament, where the decision to have a tournament and my wins are not really causally related at all, I
mhm.
still care about that flow. I still care about the decision to have a tournament, seeing a consistent view of who's winning and losing so that I'm actually inviting the best players in the world to my tournament. I'm actually ranking them correctly. Um, if things get really bad, if things are arbitrarily inconsistent, if, say, there's a major storm in North Carolina and suddenly there's just no connections between two data centers, you
Right.
can wind up getting really weird behavior when you sort of see weakly consistent systems and you use them to make decisions that you think should be with strong consistency.
Right. Which gives me another very nice segue, which is this idea of like the way you track points in these systems is you're always incrementing some counter somewhere, right? And so there seems to be sort of some sort of notion where like it should be easier to merge this kind of information. And I'm building towards this idea that you work with in collaboration with folks at Berkeley on consistency as logical monotonicity. Can you talk a little bit about where the need from this like very mathy weird concept of monotonicity comes from and why it's really useful when you're thinking about distributed systems.
So, as far as where this weird mathy concept of monotonicity comes from, I don't necessarily think it comes from a specific event or person. It's just been in the water for a long time.
For
All
sure.
monotonicity, yeah, all monotonicity says is let's say I have a function and I have inputs and outputs to that function, and there's a way to order the inputs and there's a way to order the outputs. So, my function goes from integer to integer, say, and we use less than on the integers. A monotonic function preserves that order. So if I call it with one and then I call it with two, the output will be ordered. First output is less than second output.
Right.
That's it. And it's the sort of thing that some high school math classes will teach. I don't remember when I learned it, but certainly well before graduate school.
Hmm.
What's really surprising about monotonicity is it really actually can help with distributed computing. So work with me here. Let's
Yep.
imagine for a moment that all of the storage in the world has sort of an accumulation flavor to it.
Right.
That as I'm sending things into the system, as I'm storing things, those things are getting bigger. Like if I was storing a set of colors, as I perform more writes to the system, that set of colors grows. And let's
Right.
further imagine that the primary actions I'm taking based on my storage are modeled just simply as functions. I've got some function that wants to trigger when the green color shows up.
Hmm.
I don't know necessarily why, but I like green.
Sure.
If that function is monotonic, it means that it will produce a strictly greater value when given strictly greater input.
Okay.
If that function is used to make a decision whether to do or not do something, that means it's at somewhere in there, there's a Boolean function. It's the thing that drives whatever our conditional decision is. It's going to go to either true or false.
Right.
If you put those two things together, if it's monotonic, it always goes up.
Hmm.
And if it's Boolean, it only is true or false.
Yep.
What you get is as soon as this function returns true, it's just going to keep returning true.
Right.
It
It
can't
can
get
never
truer.
become
You've already
false.
hit the
Yeah.
top.
Right.
So you've got this lock-in property where if you have some parts of your program logic that are monotonic, if your input can be modeled as monotonically growing, like say throwing things into a set, and if at any point that monotonic section of your code returns true, it doesn't matter what messages you've missed. It doesn't matter how inconsistent you are. It doesn't matter if one of your data centers in North Carolina is tragically disconnected. You won't ever have that go back to false. Even arbitrary amounts of data that you're missing won't change that decision, which allows you to make a consistent choice. It allows you to sort of pull forward or go fast for those specific parts of your system without worrying about changing the ultimate application behavior. It was true in the scenario where you missed 1,000 updates. It'll be true in the scenario where you didn't miss 1,000 updates.
Right. So it's sort of like the way I was visualizing your example is that there's only one possible transition in this the decision function, right? It goes from false to true. That's all that can ever be. Then it's always true. And so it
Right.
sort of again gives you ability to reason about the past and the future, right? Like once it becomes true in some ways, you could locally store that information and never have to query the database. Is that a reasonable thing to think about when you're working with monotone
Even
systems?
better, you can just go ahead and run the computation that's triggered by it being true.
Mm,
As
right.
long as whatever portion of your code is monotonic, as soon as it saturates, as soon as it hits whatever the top is. So if it's Boolean, as soon as it becomes true, you can just run it. You
Right.
now know all the information that could possibly be useful for that particular computation. So this is really closely related to something that's known as incremental computation.
Yep.
Incrementality is pretty popular in databases. In databases, it basically says that some parts of my computation can be run on partial data, and then the result of that can be used to update the result in the presence of new data.
Right.
So it is much more efficient than, say, arbitrary computation, where I might have to rerun everything every time I get a new piece of information in.
Right. So it's sort of the difference between reading all of the tables in your database versus being able to focus on the narrow part that actually influences the downstream computation that you cared about. And you're saying that monotone computations or monotonic systems allow for better incrementalization properties? Is
They're
that
pretty
something?
key to incrementalization. They're almost two sides of the same coin.
Hmm.
Um, if there's a how should I phrase this? Incrementalization is a little bit of a sidetrack, so I'll
Mhm.
keep this at something of a high level. If I have a meaningfully incremental computation, it means that I can perform part of a computation and cache it, and I know that that part of the computation will be the same, even if I were to repeat it on future data.
Right. I see.
So one way of viewing that in a monotonic world is that part of your computation has saturated, has hit the
Hmm.
maximum highest value. So it can't possibly change. In that sense, incrementality and monotonicity are extremely related.
Hmm.
Um, Most people don't really think of it that way. They tend to think of it more as sort of a data independent sort of thing. Like if I'm doing a for each loop over all of the information I have in a set,
Right.
It's pretty natural to imagine that adding something new to the set doesn't change what the for each loop did on everything else.
Right. So there's a disjointness property also between all of the related items. But that doesn't seem necessary, right? Because another monotone object is a counter, right? And I could potentially perform different computations based on the value of the counter,
I could, and some of them will be monotonic and some of them won't.
right? And so only the monotonic ones are sort of ones that can take advantage of this really nice property of being able to be incremental in some way.
There's actually some more details here that I think
Mhm.
might not be worth going into. For example,
Sure.
if you really want to do this incrementality, what you need is not just for the things to be monotonic, but you also need the computations that you're performing to be a, I hate to say this, to be a morphism,
All right.
or a homomorphism if you're
Sure.
staying in set theory.
Mhm.
Um, you have a function on some big chunk of data and it produces an output. If you want to do it incrementally, then you need to say, I have the first half and the second half of this chunk of data. So you run the
Mhm.
function on the first half, then you run the function on the second half, and then you have a way of joining together the results,
Right.
which means that that function kind of has to distribute over whatever it was that you used to divide the data into first half and second half. So this
Right.
distribute over data decomposition thing, it is a property of being a homomorphism.
Right. And that's true for this for each example that you gave us. Um,
Right.
so pulling us out from this like incrementalization conversation, going a little bit further up, um, all of this niceness relies on the ability to have data stores that are monotonic in some fundamental way. So how true
Yeah,
is
and
that?
applications that care about it.
Right. So how true are those two assumptions? How true are they in the current systems? How true are in the are they in this in sort of the future, right? Because I think the way you framed or the folks in the paper framed this idea was that it's a forward-looking notion, having monotonic systems. It's not necessarily something you will have today, but something people will care about more and more as we build bigger systems.
So to a certain extent, it is definitely something that's true today. Um, One example of this is demonstrated in a project that I was deeply involved in at Cornell entirely on the distributed system side. It was called Duratio. And Duratio is a system for state machine replication, which basically says you have one computer that's running a program and that computer can crash, which is bad. So you make two copies of the program on two separate computers. Now it's less likely that they'll both crash at the same time, but in
Right.
order for them to be useful, you need to synchronize them so that they take state transitions at exactly the same time. This is called state machine replication.
Hmm.
And the challenge is figuring out which requests go in which order and making sure they hit both machines at the same time. So Duratio is an underlying distributed system that does that. And we observed, like the whole point of writing that paper was that the vast majority of protocols driving state machine replication, which is a extremely standard thing that's been done in distributed systems since the 80s, the vast
Hmm.
majority of protocols driving it are monotonic already.
Interesting.
There are a ton of things in systems that have the flavor of when you see the state hit this threshold, do this other thing.
Hmm.
And those are almost always monotonic. Voting, for example, if I'm trying to
Right.
wait for a majority of votes to come in, I say, when the vote count is over half plus one, do the thing that I would do that I'm waiting for the votes to respond with. Almost every
Right.
blocking operation that you have in a distributed system is of the form, I need to make sure I get a majority of responses, or I need to see what the next message will be so I can respond to it. These are all these sort of trigger, saturate, respond behaviors. So they're all pretty easy to phrase monotonically.
Interesting. And this is also true, for example, about consistency, right? Where if you, for example, again, want to make the decision to ban a user, what you need to do, the loop you would imagine writing is wait till 50% of the data stores agree that this user should be banned, and then you go ahead. And that's, again, it has this sort of monotonic nature to it. What are some examples of things that don't fit this nice category that you still think are important to express?
There are lots of things, unfortunately.
Hmm.
So anytime, ooh, sorry, the sun just disappeared behind the clouds, so my lighting got more dramatic.
Yeah.
Um, Anytime you've got a character of rollback or revocation, things can get a
Hmm.
little bit dicey. Um, Failure detectors are a common example that people use. They can be monotonic, but they often aren't.
Mm.
So let's say that we're in a cluster of three machines, you, me, and chat. Um, So chat is going to um, go ahead and stop responding to ping, stop responding to any of our machines contacting it. And we will decide because of that, that chat's probably failed.
Right.
And so we can think of this as monotonic. We've gone from false to true on failure. But if we do so, that implies that if we were wrong, if at some point those pings come back and we're like, oh, never mind,
You have to
then
roll
we're a
back.
little
Yeah.
bit screwed. If we were using sort of monotonicity, ergo must make decisions, then we've just seen an event that goes in the wrong direction on the lattice. Our
Right.
suspicion goes from true to false.
Right. Right.
So you can, to a certain extent, re-architect systems around this. For example, in a world where people cannot unfail, there
Hmm.
would be some background protocol when a failed node contacts the processes. They get told, by the way, you're a failed node. And they go, oh, I'm sorry, I'll just fail. And then I'll get a new name and come back.
I see.
Um, but generally, when you're trying to revoke things, kick someone out of a cluster, when you're trying to change things that would have been constants, like if you're waiting for a majority of voters to respond, you need to know who the total number of voters are. Changing that changes what a majority is. So
Right.
when you think you get over a majority, if you double the number of voters, now you're under a majority. That's another one of those flapping behaviors where you went in the wrong direction.
Yeah.
All those are examples of things in distributed protocols that do come up, but that tend to not have monotonic character. The vast majority of them are going to relate to changing participation or failure.
I see. Interesting. So, what kinds of are if this is something that you want to pursue further, what kinds of extensions or changes to the model you would want to do to allow for. So one of the choices is you've described how you can certainly re-architect systems to actually be monotonic, and then they get this property for free, or you sort of somehow extend the model to talk about more of these nuanced behaviors that you still care about but don't fit nicely into monotonic behavior. Well, what approach do you think would be sort of interesting and fun to take in this space?
So when we talked about monotonicity so far, I was talking about the fact that your decision can't be revoked even if an arbitrary number of potentially decades old requests are missing from your log and that you're going to discover them later.
Right.
And that's extremely strong as an assumption. It's extremely strong as a property. It's unrealistically strong. In
Right.
practice, the systems engineers have a basic idea of how many outstanding requests they are likely to have missed and how long ago the oldest one of those is likely to have originated.
Mhm.
There's this word likely too that we also should be talking about. All of these guarantees are probabilistic. Ultimately, programs only do what you think they'll do because the computer stays on long enough to finish them,
That's
which is
right.
a probabilistic guarantee. But ignoring the probability part for a second, we know more than we are using about how these distributed systems are architected. We might know, for example, that there's an overlay or routing network, that in order to get to Ithaca, you first have to go through New York City on the internet. And we could reflect that knowledge into our protocols. We could reflect that by saying, if, say, there's a server out in Princeton, which is where I'm normally based,
Hmm.
and has seen New York City messages, it will definitely have seen all of the Ithaca messages that existed in time before that New York City message. Or actually, no, it's the other direction. If it sees an Ithaca message, it will have
Sure.
seen all the New York City messages that are the same age as it or older. Since New York City has to forward the Ithaca messages, so it has no reason to do so without forwarding its own along. And it's easy to write a protocol where New York City first makes sure it forwards its messages and then forwards Ithaca messages. And you actually see this sort of thing all the time in systems like chain replication, a very basic replication protocol. You have this, in order to do A, I must do B, and therefore doing B implies that I did A
Hmm.
um, kind of behavior. So trying to reflect that back into the guarantees we get about our system and state stability, the guarantees we get about our consistency, and using it to increase the number of kinds of computations that have that monotonic flavor, that have that we've seen enough, therefore we can go flavor, is a pretty good direction for future work for this.
Right. So it's sort of, in some ways, propagating the implicit monotonicity or the implicit monotone reasoning that protocols do for their own correctness that you want to bubble up into their implementations.
Yeah,
Is that
and just the implicit reasoning in general. I'm not like wedded to everything being monotone.
Right.
It is nice when everything's monotone, but if you view things like epistemically, a lot of the times when we're reasoning about distributed systems on the whiteboard, we'll say things like, well, replica A knows that replica B is still up.
Right. How is that possible? Well, it just saw like a message that was, 2 seconds ago, and we as the system engineer knows that there's some heartbeat protocol running, and probably this is on or something like that.
So you get these sort of implications about knowledge that if A knows B is up, therefore A also can conclude some things about the state of B. I'm trying
Right.
to find a nicer way to reflect those into language level technology would be nice. Right now, we have a pretty easy way to use a type system to detect when you are in a monotonic fragment of your program and when you are not.
Mm,
And so you can use that to take advantage of this monotonicity thing, take advantage of, in some cases, incrementality too. And
right.
the net result is your program can be fast when it's correct to do so automatically. And if you try to make a decision early on something that might get regret later, you'll get information about that from the type system and from the compiler, just to veer directly left into programming languages again.
Right.
Taking these more advanced things that I was talking about, like taking topology into account, taking predicates into account, is harder to reflect back in the type system.
Mm,
And that makes it harder to automatically determine whether you were using that information correctly. Um, but I
right.
would love to be able to.
Right. Sort of capturing these lower level physical notions and directly expressing them in the language. It's very cool. So,
Right.
switching gears a little bit, because I also do want to get to your work on programming language design, which is very cool. Um, your paper on this from PLDI on a type system for fearless concurrency, describes this new language that you've been working on to, well, achieve fearless concurrency, right? And this is a term that is also popular in the Rust community, where the notions of like having a static type system that requires you to think very carefully about ownership of values enable some of these strong guarantees that you might care about. But then there are responses from the C++ community that maybe these guarantees are not quite the right ones that you want, or the enforcement mechanisms are not the right ones. So briefly, what I would like your perspective on is what is really the problem people care about in this space, right? And it doesn't necessarily have to be sort of related to the precise solution that Rust or C++ communities have come up with. And then what do you think is missing from the space that really needs to be addressed, and neither of these languages or approaches have really addressed?
So I think the large problem here is weird non-determinism that comes from concurrency.
Hmm.
Um, let's imagine for a second that you and I are both trying to increment an integer, and we're just doing so on a traditional CPU.
Right.
So we're going to run concurrently, and the process of our code is going to be first, each of us at some point reads what the current value is, then we add one to it, and then we write it back. It's possible that under many executions, that composition of our threads will have introduced two increments into the system, that our variable went from, say, 5 to 7.
Sure.
But it's also possible that we happened to align just so that I did my read and you did my read before either of us did our write back. And the net result is that the system sees one increment of that integer. It goes from, say, 5 to 6.
Right.
This is not deterministic. And not worse than that, one of these cases is extremely rare compared to the other one.
Hmm.
Most of the time in especially systems programming, this kind of non-determinism due to racing on reads or writes,
Hmm.
is unintended, and it
Right.
can lead to errors in programs. And that's the main thing that both Rust and C++ are looking at and saying, this seems bad. People keep writing bugs where in 99.9% of times there's no race and things go in a specific order. And then in 0.1% of times they go in a different order. They break some sort of program invariant in the process. The whole thing crashes and we can never debug it because we can't figure out the precise way to interleave those threads again.
Right. Right. And Rust's specific solution in this space is you're just not allowed to simultaneously change the same memory location from two different threads, at least as long as you're in the safe subset of the language.
That's a guarantee. A different way of
Right,
phrasing that guarantee is Rust guarantee is that neither of us have access to X. We literally can't name X at the same time.
right, right. And
So
therefore
by
cannot read it.
implication,
Right,
I can't read it and write it racing with you because if I can read it and write it at all, you don't know where it is.
right. And so Why is this guarantee not the last word on this problem? Why is it something that people are not fully satisfied with?
Well, there's sort of two underlying reasons. So one underlying reason is that the guarantee itself isn't precisely what you want. For example, if we happen to know for a long period of time that no one's going to be modifying a particular variable, it's fine for everyone to read it. And
Hmm.
then if someone wants to come along and modify it, as long as they make sure that all the readers are done, they can modify it and then let the readers come back in. This is a classic reader write or lock scenario.
Sure.
And it super doesn't fit under the exactly one person can name it at a time kind of behavior that you're going to get from a language like Rust.
But
Um,
Rust does have lock primitives that allow you to express this, right? Where you can
it
have
does,
shared
but not in the
references.
safe subset.
The implementation of the lock is not in the same safe subset, but the usage of locks can be done safely, right?
Sure. And
I see.
there's a huge movement in, say, Rust towards um, this notion of API safety,
Hmm.
where there's I think it's called fiction of ownership,
Mm.
in which the actual ownership doesn't really behave like the data structure API says it does, but there are no ill consequences from that falsehood. So it works out pretty well. As long as the representation is not exposed and you can't sneak around the API, you'll have the ability to use the data structure safely. There's a huge project that we're both familiar with called Rust Belt
Yep.
that came out of Ralph Jung and Derek Dreyer for years. That's all about trying to establish what it really means to have a safe API for Rust with unsafe code implementing that API.
Right. Right.
But that's only sort of gets to point number one, which is there are some primitives of concurrency that aren't really easily expressed. Other primitives of concurrency might be like the atomics that C++ exposes,
Yeah.
where compare and swap or atomic increment are totally safe to do with concurrent writes. We were just talking about how you and I could send an increment operation to two different replicas, and that would be totally fine
Right.
because they compose well. There's no real way to expose that in Rust without making another API that says this is the incrementer guardian and that does some stuff under the hood.
Right.
Um, the
Please go
other
ahead.
major problem, the other category of major problems is let's assume for a moment that mutual exclusion is fine and you're pretty much okay with the way Rust models its database safety. In order to get that, you need to have this strict ownership paradigm where in the heap, outside of very complicated exceptional cases, every object has exactly one incoming reference to it. There's one owner. Um, and that winds up making you represent everything in your program in terms of trees.
Hmm. Right.
And
Sure.
some data structures are not easy to represent as trees.
Right.
So, like a
Famously.
circular doubly linked list is famously not a tree.
Right.
So, if you Google, just like right now, um, circular doubly linked lists in Rust, you
Hmm.
will wind up getting like dozens of hits on people being like, why can't I build this?
Right.
And there's advice like, you use unsafe libraries for this, or just use unsafe, or you know this is correct. Turn off the type system for a second, then turn it back
Right.
on later. Um, Sidebar, unsafe is not equivalent to turn off the type system. That's
Yep.
facetious.
Yeah.
Um, and this sort of expressiveness limitation really frustrates people about Rust. And I think is a large part of the energy around finding some replacement for it.
Right. So in this space, what I do want to get into your specific ideas about how to approach this problem. So can you talk a little bit about the ideas you explore, and specifically your paper talks about both dynamic and static enforcement of certain guarantees that you can use to get, again, the same kind of safety properties that you care about, while not limiting yourself to this very strong regiment that Rust enforces on you.
Right. So our basic key observation is that some data types and pointers in the heap are basically used to build an abstraction
Hmm.
and some cross abstractions. What do I mean by that? Let's say that I have a list that stores items. There'll be a bunch of data structures and a bunch of pointers in the list that are just there to like represent the list itself, back references and the head node and maybe a tail sentry that aren't really part of the list abstraction.
Right.
And then there'll also be a set of pointers that go to the things the list stores. So if I'm thinking about lists just in terms of how I'm going to draw them on the whiteboard, the
Hmm.
pointers that I really care about are the ones that point me into the list and the ones that point from the list to the objects that are stored at that list. And the rest of that internal stuff, I don't want to mess with. If I can see one of those internal links, probably the data structure is broken. Probably, especially in an
Right.
object-oriented setting, which is where most of the REST programs are coming from. That's known as representation exposure. I just saw something inside an implementation inner class, and I shouldn't know what to do about it. I shouldn't expect it to stay stable. It'll change between versions. I
Right.
shouldn't expect to know what invariants I need to maintain on it in order for the underlying data structure to be correct. So I should just not touch it. And when you look at a lot of cases where you can't represent things as trees, where there's complicated graphs or cycles, it tends to be in those data types that are part of the representation, that
Hmm.
are the inner classes that describe how a list works. In a doubly linked list, you got these references that go forward and also references that go back.
Yep.
And those backwards references are basically just used to implement reverse iteration.
Hmm.
Like they're not supposed to be some pointer that you can get your hands on. You instead have some sort of iterator or index, and you can either increment it forward or decrement it backwards, and that's all you know. From your perspective, it could just be an array.
Right.
So what you really want to do is allow those kind of complicated spaghetti graphs, but only when they're actually contained within an abstraction. In particular, by the time I step from the list to what it stores, that's where I really want uniqueness to be back again.
Hmm.
I actually do want, if the list owns the data type, for there to be one reference logically from the list into the item stored in that list. I really do want the fact that, especially if it's like a queue or a stack, when I pop it off the stack, I'm guaranteed that I now have the reference to that item and the list does not.
Right.
So you can think of it, instead of being a tree of references, like say is easy to do in Rust, it's a tree of abstractions. So
Mm.
the list is one big circle and it's got
So
lines out of it to the items that are stored in the list. And those are different big circles.
I see. So it's sort of the way you operate on this is you can open the box, open the abstraction. You can sort of muck with it, and as long as you correctly close up the abstraction by the end of the method, you get the invariance guarantees that you cared about. Is that a
Right. And
and
the
and
things
that's
you can
also true
take
of
out of the box
right.
are
Go ahead.
just the unique things, the things with unique inbound references. So I
Right.
can open up the list, muck with it as much as I want. I can take as many items out of the list as I'd like. But
Yeah.
if I try to take one of the internal representation pointers out of the list, I just get an error.
Interesting. And so the language somehow demarcates these two kinds of data types
It does.
as different. I see. In spirit, it's also very similar to how people are expected to use unsafe, right? Like the way you're supposed to use unsafe is you're supposed to muck with the correctness of your, or not the correctness, but the you're allowed to sidestep the requirements of the Rust type system and sort of carefully think about how you're using this data. And as long as the unsafe block ends and you have restored the invariance, then everything is nice and beautiful again.
It's exactly. And if you look at even in C++, how people talk about making sure that you're doing correct concurrent code, it has the same, the advice you get is of the same flavor. Strong abstractions, only ever muck with their internal state when you're inside their methods. If you go to like early Java synchronization stuff, the synchronized method must restore its invariance by the time it terminates,
So,
is like the thing it says. So this is just the generic advice on how to write correct code that deals with spaghetti references.
right,
But the thing that Rust doesn't do when you close the unsafe is actually check to see if you have restored those invariants. It just
right,
kind of fingers crossed, good luck, buddy. What
right,
my language does is enforces that you have and restore those invariants. You'll get a compiler error if you fail to.
right. The one other tricky case here is that if two of these methods that are allowed to muck with the internal representation of your data structure are executing concurrently, well, their operations can still interleave, right? And so those interleave operations have the potential of viewing those mucked up states. And so how do you make sure that that doesn't happen? Because that's again something that Rust really cares about and enforces it with this really coarse tool of just not allowing you to name that thing at the same time.
Right. Remember, we still have a tree of abstractions.
Hmm.
So we still have the case
Ah,
that there's one inbound reference into the list. So if I can call a method on a list, I'm
hmm.
crossing an abstraction boundary. I'm hitting one of those Rust-like unique references. That means you can't,
I see.
because
I
it
see.
is unique. Um,
So the abstraction, the thing you're calling the abstraction, that contains the entirety of sort of the doubly linked nature of that linked list.
It
And
encapsulates the graphy part.
I see. And this is what you call reservations versus regions in the paper, or that is something
So
different?
I think those abstractions basically correspond to regions.
Hmm.
Um, but the paper is very much written for a type implementing audience more
Mm,
than it is written for a type using audience. So I would say that thinking about reservations and regions as the paper describes them is much more about understanding how invariant preservation works in the type system
mhm.
than it is thinking about how you should like arrange your data in your program.
Got it.
What I say to programmers is if you've got a pointer that points to some sort of independent, morally independent thing that you might want to send to another thread, or that you might want to take out of your abstraction in exchange for something else, something that's clearly exchangeable, you mark it as ISO, and that guarantees that this particular reference is the only one that points into that abstraction, or that points into that sort of object, or points into that interface. And that's pretty much all I say. I don't talk about regions or reservations. I just say if you're writing a program and you've got a pointer that points to something you might want to send to another thread, make sure to mark that guy ISO.
Mm. And ISO is specifically the keyword in your language that allows for
That makes
this,
it, that has that unique tree-like reference.
right? We do have a question about this from the chat. Where Oliver asks that a typical solution that people might use. I'm basically going to describe this as the arena allocator solution, where you store your graph as an array, and then you have integers floating around, raw integers that you can just index into the graph representation, which is the array. And Oliver asks, like, how do you feel about the solution? Does this hide the problem? Is it sufficient? Are there like obvious challenges?
It very much is just hiding the problem. So what you're doing by that is you're saying, I would really prefer to see memory as just this big array, and I'd really prefer to see pointers as just
Right.
integers. So you're just back in the C memory model.
Yeah, and it's this makes perfect sense, right? Like if you just have a big array, well, now you're working with the linear memory. One of the things I did want to talk to you about is like this kind of pattern is surprisingly common in especially the high performance subset of the Rust ecosystem. A lot of people like rolling out arena allocators or slab allocators, to the point where like, if for example I build a compiler, like the right approach is not to use Rust-based pointers, but to actually just allocate each node in my intermediate language as a particular array, and then sort of index into it because that's faster. You get sort of spatial locality and all this stuff. And so that the fact that so many people are willing to use it and especially wanting to use it points to some sort of limitation in the language. I'm curious if you have thoughts about why, beyond just correctness, I think it's also a performance thing, why people want to use these kinds of abstractions and what languages can do to be better at supporting these abstractions safely and correctly.
So I want to disentangle two different things here. One of them is that you want control over the allocator.
Yep.
So you happen to know what data locality you'll need. You happen to know what you want to have as pack representation. Maybe you have clear aligned access or fragmentation problems that makes a slab allocator better.
Mhm.
This doesn't imply that you want to have some sort of sharing of references to the objects allocated out of that allocator that is distinct from what REST guarantees.
Yep.
It just says that you want some allocation behavior that has semantic intent.
Yep.
And while you can actually override the allocator in Rust, it is much, much harder to do it there than it is to say do it in C++,
Or
where you can
Zig.
just register a new backend for new and you're off to the
Right.
races.
Right.
Um, and I think that's a bit of a limitation of Rust, but one that I would call as a library-like limitation. It's
Mm.
not particularly difficult to imagine how to keep Rust's principles the same and introduce the ability to create an allocator for a set of data types that has an allocate and deallocate method on it. The deallocate method is automatically called whenever the pointer goes out of scope. And we generally enforce the only one pointer at a time rule outside of the allocator. So the allocator holds some pointers internally for its internal state, but the application only has one pointer to each, say, slot in a slab.
Right. So
Um,
I was going to push back on that point specifically a little bit because I think one of the things that ends up happening a lot more when you're in this regime is you can actually name those slots, as much as you want. What you lose in the Rust system is the capability to dereference, right? So if you think about this arena, let's say I have like all of the variables in my language sitting in a big arena. And I have pointers to those names and their reference from other AST nodes in the compiler or something. What you need to actually get the data associated with that variable is the capability to dereference from that arena. And that's something that you are not allowed to do if someone else is mutating that arena in Rust. And so it really does become your solutions end up being you reference count the arena or you use ref cells or something, some sort of hack to go around this to roll back to
Again, there's a conflation here. So
mhm,
if the application logic outside of the allocator needs to be able to hold two mutable references simultaneously,
mhm,
that's one thing. If the reason we need to get around that is because the arena needs to hold a mutable pointer and the application needs to hold a mutable pointer, that's a library failure
mhm,
because you should be able to have the illusion of safety there. You should be able to say the arena is a concrete abstraction, the arena has fiction of ownership, and the arena is correctly implemented such that a mutator outside of it will never be able to witness mutation inside of it. That's got the same guarantees as like the doubly linked list libraries that you write in unsafe Rust or any of the concurrency libraries that you write in unsafe Rust. But
right.
when the application itself, the like logic the programmer is writing, actually needs to have two potentially dereferenceable references simultaneously, that's where Rest breaks down. That's where like just making a good library where it's internally unsafe and we've put a boundary in front of it, um, and we enforce safety at the boundary manually. Like it really, really breaks down if the application needs two simultaneous mutators. And for a lot of, say, HPC stuff,
Mm,
this is really, really difficult to get around because a lot of HPC stuff has the flavor of take this big data structure, split it up a bunch of ways. Everyone concurrently operates on their sections of it and come back. And it is not the case that when you've split it up a bunch of ways, there's no pointer path between various parts of this graph. It's just the case that the application never chooses to use them. And Rust isn't that smart. Rust is going to try to make you prove that you can't actually follow a mutable pointer path,
right. It'll
not
force you to
just that you
split it
don't
into
intend to use
literally,
it.
right.
Yeah.
It'll force you
So if it's
to,
tree
yeah,
structured, where like the splitting is evident in the data, and I can give you the first third of the data structure by giving you a reference that only points to the first third of the data structure, you're grand, you're excited.
mhm,
But it's also tree structured. So now it's this crazy big pointer rich thing. But if
right,
whereas if it's matrix structured and it's just like I hereby solemnly swear to only use numbers 0 through 5 when I call the
right,
index method, Rest doesn't have any way to reason about it.
right, right. Interesting. There's one more audience question that I want to follow up with, and then we should wrap up. The question asks, you alluded to monotone functions as functors earlier. Is there anything else category theoretic that you work with for concurrency or databases?
I will say that you can do a lot of databases categorically. Like there's notions of pullbacks and pushouts and completions for handling absent data in joins, for example.
Hmm.
Um, but that I personally don't tend to work in that space. Um, I try to write papers that have the shot at getting read by both the systems audience and the PL audience. And the systems audience generally can't assume category theory.
Yep.
So even sometimes where it would make sense to use more categorical interpretation of whatever I'm doing, I don't. And I use some like
Right.
boneheadedly syntactic versions of it. And the proofs as a result, instead of just saying that's adjoint to that, move on, have these like really long inductions and it takes 10 pages to get
Right.
through them.
Right.
I'm carrying all of my abstractions with me as I go. It's a little bit labor intensive, but it does mean that category theory isn't a prerequisite for reading the work.
Right.
And
So
it's a trade-off there.
yeah, and you mentioned this insight about how thinking about morphisms allows you to sort of think about incrementalization correctly. And just to put on a category theory hat, I wouldn't call it my category theory hat, but what you're doing is you're using category theory to derive conclusions about the space and then translate it into a language that systems folks can understand, right? You have internally inside your head a morphism between ideas that you're using to translate concepts so that systems folks can read them and understand them. So one, this sort of describing perhaps a principle or a taste thing that you have about like yes category theory is perhaps a good tool for me to think about, but at the end of the day, back to where we started, systems problems are the problems you care about solving, and some people maybe won't care about it if you write it like that.
Yeah, one of the things I'm actually famous for saying in front of my students, which to the point where if they made a bingo board about me, I'd probably be on it,
Hmm.
um, is you're going to hate this, but I think it's a monad.
Right, right. Well, I
But
think
again, that's a race by the time it gets to the papers.
that's right. That's a good place for us to wrap up. There are two other prompts I have for you, and you have the floor. I think first, again, we're doing this theme of talking to junior faculty who've started working in PL and systems. You started at Princeton, and I assume you're building your lab and recruiting students. I just want you to have the opportunity to pitch some of your work that you're doing and thinking about, and what kinds of exciting problems students can work with you on if they come to Princeton.
Okay, so if you go to my website, there's a looking for students page that will always describe some active projects that are recruiting, which will stay up to date, unlike this podcast. If you're listening to this in the year 2027, I presume I look older and also everything I'm about to say is over. Um, Beyond that, let me pitch one particular project that I'm quite excited about today. I really like the ability to write programs against distributed storage. I think it's intuitive. I think it allows you to have lots of different applications that communicate via storage as an abstraction. I think it's easy to explain to incoming programmers how you can just read and write like variables, and that corresponds to reading and writing variables. But what I don't like is that this implies that I need to go up and beg Amazon very nicely for some access to its underlying cloud storage ecosystem. What I really don't like is that I wind up getting this vendor lock-in
Mm.
where I have to build my application around the APIs that are almost intentionally different across different cloud hosts. What we're trying to do now is build out a new both language and systems backend focused on weak replication and almost peer-to-peer style replication,
Mm.
where we don't need there to be some big monolithic database to enforce consistency. You can just sort of spin up ad hoc servers, have them join the cluster, and preserve the behavior of it looks like there's a giant storage system in the sky. So it's really a have your cake and eat it too sort of scenario. You can build collaborative applications, your Google Docs, your Gmails, as though you had this big cloud run by several small, not small, a small number of large companies. But you can implement it as like the original dream of the 90s internet, just a bunch of schmoes connecting together, keeping their computers on long enough to exchange data.
Wonderful. That sounds super exciting. And our final question always is, what are three papers that you really enjoyed reading? They can be within your area, they can be in biology, they can be whatever you think is a cool set of papers to read for people listening to this.
All right, well, I'll give you one in biology, one in my area.
Wonderful.
Um, so a programming, I like weird DSLs. I like when type safety means something different from just the program doesn't crash.
Hmm.
And a particular paper that I read a while ago that embodies type safety is safety in a different respect is called BioScript. I
Mm.
think this is out of Mohsen Lassani, who is at Santa Cruz now, maybe UC Santa Cruz. He's in one of the UCs. I think he used to be at Riverside or Irvine and moved. Not super important. BioScript's purpose is programming something called microfluidic controllers,
Yep.
which are tiny little electrically charged disks with little droplets on them that use electrostatic repulsion to move the droplets around. And it automates chemical reactions. And this programming language has a type system that can reason about chemical reactions, which is great
Yeah,
because in
it's
that
kind of
language,
funky.
it means that type safety implies literal physical safety. Your program
Right.
will fail the type check if you accidentally make mustard gas.
Oh, wonderful. I thought it would be something like, the molar quantities required for your chemical reaction to actually succeed is checked at compile time, as opposed
No,
to
it's stuff like reasoning about how long the like little droplet trail will be when you move things around so that you can tell if
ah,
you're about to lose the game of Snake
I
that
see,
is
I see.
implicitly being played on this device.
Right, right, of course, I see.
um, which is pretty fun. So that's paper one, BioScript, always a fan.
Mhm.
Paper number two, I sort of chose where to do my PhD based on it, is the Fabric paper
Mm.
out of Cornell. This was by Jed Liu. Fabric is in a pre-cloud world and it imagines a huge, non-replicated, decentralized space of objects where people communicate by calling methods on each other, and
Mhm.
ask the question of how the heck do you handle security in that setting? everyone's just connecting and authorizing themselves to do whatever they feel like. What does that mean? How do you make a good, reasonable programming model out of this just everyone's directly connected kind of ecosystem? I love the fabric paper. Um, and one of the other papers that really got me into research is the Singularity operating system.
Mm, a classic.
So Singularity was a please, let's just reimagine how processes in an operating system should communicate. How do they exchange messages? What does it mean to have resources provided by the operating system and to exist in tenancy with other processes? So all of these papers are kind of old. Certainly the second two are like papers that got me into grad school.
Mhm.
But they all share a what if mentality. How could we redesign this thing that we've been assuming works a particular way for a long time? And the hallmark of my favorite papers are the ones that throw out assumptions, find a new point in the design space and say, do we like it here? Here seems nice.
Right, and that seems crucial to be innovative in a space like systems, right? Systems are defined by the trade-offs that you have, and if you don't understand the trade-off, and if you're not willing to break from the existing norms and design something radically different, how are we going to make progress? Well, this has been a super exciting chat. Thank you so much, May, for taking the time. Once again, May is in the Princeton CS department. If you're excited, go look at the webpage. It's in the chat and I'll be on the transcript. Yeah, thanks for coming, May. So I'm going to stop the recording now.